Okay, this video is a review of some of the linear algebra that we'll need for multivariable calculus. So some linear algebra review. That we'll need for multivariable calculus. And we have Rn. So if n is some positive integer, it's the collection of all points with n coordinates, right? So it's just collections of n numbers ordered, instead of ordered pairs, they're ordered collections of n numbers. So such that x1 through xn are real numbers. So these are called n-tuples. Notice that this definition is not geometric, right? It's not, I'm not defining Rn in terms of arrows or anything like that. But in the case of n equals 2 or n equals 3, then you can think of R2 as an arrow starting from the origin. So for instance, the n-tuple, and typically in linear algebra, we'll write these as a n by 1 matrix, right? Like this is a column vector. That's the convention that makes multiplying a matrix by a vector easier if you just think of that vector as an n by 1 matrix. So if you have this vector 1, 2, it can be identified with this arrow that goes right 1 and up 2. And in R3, if you have something like, I don't know, like 2, 2, 2, you can identify it as 2 along the x-axis, 2 along the y-axis, and 2 up, right, along the z-axis. And we have special names for certain vectors, E, or I guess I, often, I, or I hat. It's just 1, 0, and it's usually written as E1 in a linear algebra book. And J hat, in this case it's 0, 1, and that's written as E2. And in R3 you have E1, E2, and E3. So in general, EI is just a bunch of zeros, but then you have a 1 in the ith place. And then the rest are all zeros, right? So for instance, in R4, you have E1, which is 1, 0, 0, 0, E2, which is 0, 1, 0, 0, E3, which is 0, 0, 1, 0, and E4, which is 0, 0, 0, 1. And any vector in R4, okay, it's just A, B, C, D, is a linear combination of these vectors. So it's AE1 plus BE2 plus CE3 plus DE4. And these vectors in Rn, okay, the set E1 through En is called the standard basis of Rn. Okay. And you have maps. So once you get familiar with Rn, there are functions from Rn to Rm. And the ones that are of interest in linear algebra are the so-called linear transformations. So a function t from Rn into Rm is called a linear transformation if for all vectors v1 and v2 in Rn and all scalars meaning all real numbers, C1 and C2, T of C1 V1 plus C2 V2 is equal to C1 T of V1 plus C2 T of V2. That's the linearity property. So this condition is very important. That this is true for all vectors V1 and V2 and all scalars, emphasis on the word all, scalars C1 and C2 real numbers. And this condition makes the functions restricted in some way, because once you know where it sends E1 through En, then by the linearity, that determines where it sends any vector in Rn. Precisely because any vector in Rn is a linear combination of the E1 through Ens. Oh, and by the way, this condition is equivalent. So this condition star is equivalent to, sometimes it's broken up into two conditions. So that T of V1 plus V2 is T of V1 plus T of V2 for all V1 and V2 in Rn, and the second condition is that T of CV equals C times T of V for all scalars C and all vectors V in Rn. Right, so it's equivalent to having both of these. So depending on the textbook, one or the other is given as the definition of linearity. I mean, the first condition clearly implies both of them, because the first condition, okay, so number one is just the case when C1 and C2 are both 1, and then the second condition, the multiplicative part is just the case when C2 is 0, okay? And conversely, if you have these two conditions, 1 and 2, that implies the first condition, because, so if we call this condition, okay, let's give the proof. If we call this condition double star, or both of them, then 2 implies 1, because T of C1 V1 plus C2 V2, well, this is a vector and that's a vector, and so by condition 1, this is equal to T of the first vector plus T of the second vector, right? So this is by 1. And then by 2, each of these, the T of C1 V1 is just C1 T of V1. Right? So this is C1 T of V1 and then plus C2 T of V2. And so we see that T of C1 V1 plus C2 V2 is C1 T of V1 plus C2 T of V2, which is precisely condition 1. Okay, and typically a bunch of examples are given, and it turns out that these types of functions, or transformations, mappings, okay, they all pretty much mean the same thing. Typically the word function is used when the codomain is R, right? So like f of xy equals sine x plus y or something, rather than a vector valued function. So usually what, we're thinking of a transformation as taking Rn into Rm, we usually use the word map or mapping to describe that. but it's more of a connotation. I mean, strictly speaking, it is a function. So these are related to matrices. How? Because every matrix, every m by n matrix A defines a linear transformation say TA from Rn to Rm by the definition TA of a vector v is just by definition A times v. Right? So if you multiply A by a vector v, you get some vector in Rm, and the linearity property that you need to check in order to check that this is a linear transformation is just the property of matrix multiplication. And conversely, whenever you have a linear transformation, okay, if we start with a linear transformation, given a linear transformation, T from Rn to Rm, there is a matrix A such that for all v and Rn, T of v equals A times v. And here, this is the function notation, right? It's T of v. You plug v into T, so to speak, and then this notation is matrix multiplication. It shows up here too. It's A times v. And how does that work? How do you get a matrix if you have a function from Rn to Rm that has the linearity property? So what you do is you form the matrix, an m by n matrix, whose jth column is T of Ej. So for instance, if T is a linear transformation from R2 to R3, let's just make this up. So let's say that T of xy equals x minus y, x plus y, 3x. Okay, so how do you get a matrix from this function? So you take T of E1, that's T of 1, 0, and that's equal to 1 minus 0 is 1, 1 plus 0 is 1, 3 times 1 is 3. And so you get a matrix where the first column is 1, 1, 3. And then T of E2 is T of 0, 1, and that's 0 minus 1 is negative 1, 0 plus 1 is 1, 3 times 0 is 0. So the second column is negative 1, 1, 0. That's the standard, it's called the standard matrix of T. Okay. And we can even check that this is correct, because if you multiply this matrix, so this is a 3 by 2 matrix, right? So then it, if you multiply it by xy, you in fact get x minus y, x plus y, 3x plus 0y. And that's exactly what T of xy is by this definition. Okay, so linear transformations from Rn to Rm in some sense are very nice because they can be represented completely by a matrix. Now let's look at what we can get from this matrix. So the main thing we're interested in is the image of the linear transformation. In other words, if you have this linear transformation, this example, how do you describe all the output vectors of this map? So when you plug in a vector xy, you get a vector in R3, x minus y, x plus y, 3x. Now is that, right, if you plug in all the vectors in R2, right, into this transformation T, and you get all these output vectors, is the collection of output vectors R3, or how do you, is it a line, or what kind of shape do you get? And the answer is that the image of T is the span of the columns of A. And the span of the columns of A is called the column space of A. So what's going on is that T, okay, so T takes vectors in R2 and spits out vectors in R3, right? And what happens is that the first basis vector E1, that's going to go to the first column of A. So E1 goes to 1, 1, 3, which is like here, say. So this is T of E1, that's 1, 1, 3. And E2, okay, when you apply T, this function T is taking vectors in R2 to vectors in R3, right? The output, so here's E2, the output is this the second column vector, negative 1, 1, 0, which is, okay, so here's the x-axis, here's y, and here's z. It's like something like this. So this would be T of E2 is negative 1, 1, 0. Now these two vectors are going to span, in this particular example, they're going to span a plane, right? If you take all linear combinations of these two vectors, you get this plane, and that plane is the column space. It goes through the origin. Okay, it goes through the origin. It's a plane through the origin, and that is the image. The collection of all vectors on this plane is the image of T. And that's because any element of the domain is a linear combination. Like any vector in R2 is has the form C1 E1 plus C2 E2, and by the linearity of T, that corresponding output will be C1 T of E1 plus C2 T of E2. Right? So if you take, in the domain like 1 of the blue vector and 2 of the purple vectors and plug that into T, then the output will be 1 of the blue output vectors plus 2 of the purple output vectors. Okay, and if you think about the span of these two vectors, the blue and the purple output vector, it's a plane. The span is a plane. And it's a plane through the origin. Okay, and the dimension, so I don't want to spend too much time going into this because it's, maybe I should explain anyway. So the output, the image of T is an example of something called a subspace of R3. So in general, a subspace of Rn is a subset. It's a non-empty subset. Okay, so it can't be the empty set, if you know what the empty set is. It's a non-empty subset of Rn, okay, with the property, with two properties. The first one is it's closed under vector addition. So let's call this subspace W. So closure under vector addition means whenever you have two vectors, v1 and v2, that are in W, the sum, when you add them, right, you're going to get this vector, and the sum has to be also in W. whenever V1 and V2 are in W, the sum is also in W. Okay. And that's closure under vector addition, and then the second one is closure under scalar multiplication, which is whenever you have a vector, every scalar multiple of that vector, so whenever you have a vector in W, all the scalar multiples of that vector also have to be in W. So whenever V is in W, and C is a real number, CV is also in W. So in practice, now this implies in particular that if you take, C equals 0 in the second condition, that says that whenever you have a vector in W, which you do because it's a non-empty subset, whenever you have a vector V in W, any scalar multiple, including 0 times W, is in the subspace. So 0 times, so you take C equals 0 on V in W, you get that 0 times V, which is the 0 vector, is also in W by condition 2, closure under scalar multiplication. So every subspace of Rn has to contain the 0 vector. And so for instance in R2, what do the subspaces look like? Well, it has to contain the origin, we talked about that. And whenever it contains any other vector that's non-zero, by property 2, it has to contain all scalar multiples of this vector. So it means that it has to contain the entire line. Okay, so a subspace of Rn cannot contain like a ray. It can't contain something like half of a line. I mean, if it contains the vector, it has to contain the entire, all scalar multiples, okay, all real scalar multiples of that vector. So once you have a vector in it, it has to contain the line through that vector. Now, if your subspace of R2 is just this, then that would be a subspace. I mean, if a line through the origin is a subspace. So you can have 3 different types of subspaces in R2. You can just have the origin. Okay, if you just have the set consisting of the origin, that is a subspace. And you can also have a line through the origin, like this line. Or you can have all of R2. Now let's say that you had a subspace of R2 that wasn't this line and it wasn't just the origin. How do you know it's all of R2? Well, because it would have to contain some other vector, and if it contains the blue line and it contains this green vector, it must contain, well, by property 2, it must contain all scalar multiples of this line, but it also has to be closed under vector addition. Whenever you take a vector on this blue line and a vector on this green line and add them, the result also has to be in your subspace. And if you think about what that tells you, it implies that you'll get all of R2 because these 2 vectors, like if you have a vector on this blue line and this vector on this green line, those 2 are linearly independent, and they will span R2. So subspaces of R2 are relatively simple. They're just, okay, lines through the origin, or R2, or the 0 vector. And in R3, you have, by the kind of similar reasoning as to R2, you have the origin, or you can have a line through the origin, or you can have a plane through the origin, or you can have R3. So 4 kind of types of subspaces. And there's an infinite number of subspaces of R2 and R3 because there's an infinite number of lines through the origin, and in R3 there's an infinite number of planes through the origin, right? But whenever you have a line through the origin, we call it one-dimensional. So we say that the subspace, we shouldn't say equals. um, the subspace that just consists of the origin, this is called this is a zero-dimensional subspace. A line through the origin is a one-dimensional subspace, and R2 is two-dimensional. And similarly in R3, this is the zero vector subspace is zero-dimensional, a line through the origin is one-dimensional, a plane through the origin is two-dimensional, and R3 is three-dimensional. Okay. Now what is the precise definition of the dimension of a subspace? Well, to do that, to talk about that, we have to introduce the concept of a basis. So a basis for a subspace is a set of vectors in the subspace. So let's call the subspace W. Set of vectors in W with the following properties. It's linearly independent. And spans the space. So for instance, if you have, let's even just look at R1. The elements of R1 are just vectors with one component in them, and you can just identify those with numbers. So we'll just identify, something like this, we'll just identify it with the number A. Now any non-zero number is a basis number. C gives a basis, the set consisting of C of R1. Right, you just pick any number C. Let's just pick it to be negative, because any real number is a real number multiple of C, right? I mean, so to check that it spans R1, just take any real number, say R, and write it as a scalar multiple of C. Well, that's just going to be C times 1 over, it's just going to be R over C. Right? So this shows that every real number is a linear combination. It's a scalar multiple of C. I should probably, to make it match the notation more, it's probably better to write it as R over C, C. So that I'm taking a constant multiple, I'm taking a scalar multiple of C. Okay, and in R2, you have any collection of two linearly independent. So in R2, it just means non-parallel. Any set of two linearly independent vectors is a basis for R2. So you can just take, this vector and that vector, say, right? V1, V2. So for instance, the set V1, V2. It's linearly independent, and those two vectors span R2. And in general, Rn, it's a theorem that you can take any set of n linearly independent vectors is a basis for Rn. In particular, the standard basis, right? That's the simplest basis. The set E1 through En is a basis for Rn. By the way, in some books, so here I'm defining a basis or a subspace to be a set, but some books define it to be a list, an ordered list. And the only difference between a set and a list is that in a list, the order matters. So for instance, if you say E1, comma E2, that's different than E2, comma E1. And so that's something I would call an ordered basis. An ordered basis would be a basis, but then you have to pay attention to which vector comes first and which vector comes second, etc. And sometimes you need an ordered basis when you're talking about, say, the change of basis matrix, um, and giving coordinates to vectors. Then the order in which you list the vectors actually matters. Anyway, it's not a big deal. It's just something to keep in mind. And the theorem is that any two bases for a subspace, so let's say you have a subspace W of Rn, then any two bases for it have the same number of elements. So that's the theorem. Any two bases for a subspace W of Rn have the same number of elements, and once we have that theorem, we can define the dimension of a subspace. We define the dimension of a subspace of Rn to be the number of vectors in a basis of W. And why did we need that theorem to make this definition make sense? Well, because if you didn't know the theorem, then you can pick a basis for W and someone else can pick a different basis for W. And if they have different numbers of elements, if your basis has 5 elements and that person's basis has 16 elements, then it wouldn't make sense. I mean, would the dimension be 5 or 16, right? In math, the lingo is that the term dimension would be not well defined, meaning it depends on the choice, in this case, of a basis. And in this case, but the theorem says that it doesn't matter which two bases you have. Now, any subspace is going to have an infinite number of bases, as long as it's not just like the zero vector, because if you have a basis, then you can always just scale the vectors in that basis to produce a different basis. But the key thing is that they have the same number of elements. Okay, so two different bases are going to have different vectors, right? But they will have the same number of elements, and you just count how many vectors are in one basis compared to another basis. They will have the same number of elements, and that number is called the dimension. And since Rn has the standard basis, right? This has n elements. Therefore, the dimension of Rn is in fact n. And if you have a plane, it's spanned by two independent vectors. So a plane is two-dimensional. A line is spanned by one vector, and so a line through the origin is one-dimensional. So the concept of a basis gives you the concept of the dimension of a subspace. Okay, one more thing in the review is the rank of a matrix. So the rank of a matrix, what's that? Well, there's many different ways of defining the rank, but the way I'll define it is if you have a matrix, if A is an m by n matrix, okay, so you look at the columns, its column space, its column space is, okay, the span of the columns, and it has a dimension, because it's a subspace of Rm. It has a dimension, and this dimension is called the rank of the matrix A. In other words, it's the dimension of the image of the linear transformation associated with A. So for instance, if you have, okay, let's just take a really simple matrix. If you just have this 3 by 2 matrix, this has rank 0 because the image is just the 0 vector in R3, and that the subspace of R3 consisting of the 0 vector has dimension 0. Maybe that's something I should have mentioned. When you have the 0 vector being a subspace, right, or technically the set consisting of the 0 vector, the concept of a basis is a bit maybe the definition of a basis doesn't apply in that case because you have to talk about linear independence and spanning. But in that case, in the case of the so-called 0 subspace, we just define the dimension of that to be 0. Okay, and if we're pressed, we would say that a basis for that is the empty set. But that's not something we worry too much. If you just say that a basis is an empty set and the 0 subspace is 0 dimensional, that is correct. Okay. We could just define the word dimension in that case to be separate. So anyway, so this matrix has rank 0, and if you have this matrix, 1, 2, 3, 4, 8, 12, then I see that these two column vectors are scalar multiples of each other, and so I really have one linearly independent vector, so my column space has rank 1. The column space, has dimension 1, therefore the matrix A has rank 1. And if you have two linearly independent vectors like this, right, 1, 2, 3 is a vector in R3, and 4 to 5, 6 is a vector in R3. Those two vectors are independent. So this matrix has rank 2. Okay, and in general, the rank is going to be the maximum number of linearly independent columns you have. So you can think of the rank of A as the maximum number of linearly independent columns, because those linearly independent columns are going to span the column space, and therefore it will be a basis. So for instance, if I had 1, 2, 3, 4, 5, 6, and then like 8, 10, 12, right? These first two vectors are linearly independent, but the third vector is just 2 times the second one. And so I really have 2 linearly independent columns, and so the rank is 2. Right? Because if this is V1, that's V2. I have that V3 is just 2 V2. Or if I just replace V3 by any linear combination of V1 and V2, the rank will be 2. However, if I had a matrix that was like, 1, 0, 0, 0, 0, 1, 0, 0, 3, 0, 1, 0, or something, then I see that I have 3 linearly independent columns here, here, and here, and so the rank of this matrix is 3. Okay, and if I replaced the 0 by, say, a 5, what will be the rank of this new matrix? It will still be 3 because this third column is still a linear combination of the first two columns, right? It's 5 of the first vector plus 3 of the second one. So that's the rank of a matrix, and this pretty much concludes the review of the linear algebra that we need for multivariable calculus. Okay, but all this stuff is covered in the standard course in linear algebra, and okay, I didn't go into the details of the definition of linear combination and span and base and linear independence. Okay, but that's something that, let's see, I think I already have videos on that. So I'll just leave that here. Okay. And if you want a place to review this stuff, you can just consult any book on linear algebra. I mean, the book by Lay is a standard linear algebra textbook, and that has everything that I explained in this video. Okay, thanks.